So welcome everybody. Thank you for joining me today. I appreciate it. It's not easy to get up after the party last night, and if you stayed up late. So it's great to see so many people showing up at the first session. And today I'm going to talk about software updates on embedded Linux devices. And to give you a quick overview of the session, so we'll go through some introductions. I'll talk a bit about embedded Linux, so we all have a common understanding of what that is and what I mean when I say embedded Linux. Then we will take a look at some software update methods that are commonly used in embedded Linux. And lastly, I will try to cover some existing solutions that exist, primarily focusing on open source solutions. So which are easy to get started with, which you can use to update the software of embedded Linux devices. And primarily, previously, when there were no existing open source solutions, everyone was rolling on their own for each project or for each product. You would design your own custom updater. Maybe it had the OTA capabilities, and it was often like an afterthought. It was not something that you launch your product and then you realize, oh, I need to update it once I deploy it somewhere, right? And that's why there is an ecosystem nowadays of open source solutions that try to solve these problems, and why I like to talk about them. So quickly about me, my name is Mirza. I have approximately 8 years working experience, primarily with embedded Linux. I do have some background in automotive because I'm based in Sweden, in Gothenburg. And it's kind of hard to avoid automotive if you live there, with Volvo and Volvo trucks and so on. And I primarily worked with like board support package development, which means I've been very close to hardware and like Linux kernel drivers and stuff like that, U-boot and build systems and so on. And so I'm not so much of a developer that I'm working on applications and so on. So I'm more on the platform side of things usually. And I do work, and this is like a disclaimer or what, I do work at Mender.io, which is an open source solution to do over-the-air updates. So I will be talking about Mender, but I will also be talking about other solutions as well. But just so you're aware that I might favor one of these if you ask questions. So embedded Linux is pretty much everywhere nowadays. So I kind of like seeing these failures in real life, where you realize that here you have a trash can that has kernel panic for some reason, or like a faucet for some reason. So I mean, there is software in everything nowadays, and like in the future as well. There's more and more software in all of the kind of components. There's another example, and this one I took myself, which is like a science exhibition in Gothenburg. So you see, there's a problem there with Saturn, I think. It crashed for some reason, and you could see it was like a Raspberry Pi or something. So I kind of enjoy when you spot these kind of things, and you kind of realize that there is Linux like everywhere. But I mean, areas of usage, it's fairly common in transportation, public transport, fleet management, tracking, predictive maintenance, and this is where I have quite a lot of history in working in that field as well. Automotive, infrastructure and things, appliances, routers, TVs, I mean, so and in case I missed any of them, just to say that there's this thing called the Internet of Things, and I don't know really what it is, but it means taking all the things in the world and connecting them to the internet. And chances are pretty high that they are running Linux, right? So it's everywhere. But there is some problems moving to this things world. I mean, Linux has been a very dominant factor in servers for a very long time, also in PCs to some degree. But the embedded environment is quite different to how it was used before. And some like characteristics of the embedded environment. Usually devices are installed somewhere or in various locations that might be hard to reach. It could be in the jungle in the Amazons, or it could be top of the mountain, or under the sea, and it can be in vehicles that are moving. So typically it's hard. So if you want to do something physically to the devices, it would be very costly to travel around and to all of these devices. So they are typically remote. Long expected lifetime. Typically, when you design a product that you ship in some form, you kind of expect it to live for a certain time, and especially like automotive, there you have quite longer than 5 to 10 years, but generally like 5 to 10 years is pretty common. Unreliable power. That's something that's also very common in embedded Linux environment or the embedded environment in general. So you have devices installed in vehicles, and yeah, it's pretty obvious that you could lose power at any time in a certain situation. So you kind of need to think about this. And then you have unreliable network. Maybe it's a 3G connection, maybe it's 2G or GPRS connection. And if it's a moving thing, you can like enter a tunnel and lose connectivity and so on. So there's a lot of moving parts, or there could be. And I don't know if I need to say this, but if you have software, and I'm assuming most people in here are some kind of involved in writing software, you know that there will be bugs, there will be exploits, there will be all kind of things. So it's a pretty general requirement nowadays that it must be updatable in some form to fix those bugs and vulnerabilities. But also it is being shown that it's quite a competitive edge if you're able to provide like new features by simply providing updates to the software, meaning you could launch your product earlier with some features missing, and then you could like provide the software update to add new features later once the devices are deployed to the field. So yeah, must be updatable. It's pretty. This is a pretty common graphics that we use to just explain a bit the software stack or the system stack of an embedded Linux system. So you typically have some kind of hardware, a board support package, that's drivers and everything for your hardware, operating system. And this is also where we see like the OTA capability should be in the slower end of things. You have some kind of middleware, and up here you have your product differentiation. So that's your custom application that does something that provides value to people or to customers. And here it's pretty much a very high. This is a very costly. So typically you don't really want to do this. You want to do this up here. And that's why a lot of people, and especially in embedded Linux, you focus on open source down here. You try to source some hardware that it has a well-supported software stack, so you don't have to do all this on your own, right? So you can start writing your application and focusing on that and spending your resources. And that's why like OTA updates are also, this should not be like something application developers should need to do. They could reuse an existing solution and focus on, and of course there's some obvious benefits, lower cost of course, shorter time to market if you can focus on your application and don't worry about the lower stack. so much. Any questions or comments on this? Okay. So there's software updates. There's two ways essentially to do it. Software update on site, or that means you have some kind of physical access to a device. And it usually involves a technician or someone taking a flash drive, USB flash drive, inserting it, and rebooting the system or something, and then it's going to take the update and so on. But I mean, obviously this doesn't scale well, nor it's not always the case that you have physical access or easy physical access to devices. And that's why software updates over the air becomes interesting. If the device is connected, of course, that's a requirement. Then you don't really have to have easy access to the device, but it introduces new challenges if you want to do this over the air. Then there is, we'll talk a bit more about it later, but you cannot fix it if it goes wrong, right? If something goes wrong, and there's no easy way to fix it, you need to send someone to that device to fix it in that case. So there has to be some kind of fallback mechanisms and so on in place. But you also would want some kind of management when you provide over the air. So you have traceability, when did I deploy software to this, and if something goes wrong, you have some kind of log of that, and what current versions do I have in my fleet of devices and so on. And in some cases, you also want to do controlled rollouts. And that means maybe not deploy the software to all of your devices at once, but maybe a small percentage. You start off with 5% of the devices, ensure it works, and then you can continue deploying it. And this is this is how I kind of use Android as an example later as well, but they don't ship the update to everyone at once, but it's kind of isolated regions where they test things out and then gradually deploy it to everyone. So just some couple of, to mention, inside an embedded Linux system, you have some kind of components that are software that you typically want to update. So at the bottom, you have the bootloader that does some low-level stuff to get the system running. And this is a component that is typically hard to update securely or robustly, unless you have some kind of hardware support or hardware redundancy. So in most cases, you avoid updating bootloader. You have, for example, the Linux kernel. You have a device tree that's ARM thing for hardware description. And then you have the root file system that contains the operating system and your applications and so on. And typically, you would like to update all of these. And I will be talking a bit about images. And to me, an image is when you bundle all of this into, say, a file system image. So you have your distribution, applications, the Linux kernel, device tree, everything in one single file system image. That simplifies things if you want to do updates. We're going to get back to that. So there are some minimal requirements when you're doing updates in general or over-the-air updates. You want to be able to update all the components, so even the Linux kernel, the file system, the device tree. But typically, bootloader is a very application-specific thing. So it depends on your hardware and how, if it's possible to do it robustly, I would say. You don't want to render the device unusable. A brick is commonly the common term. So even if you lose power during the update or lose network connectivity, you still want to have the device should only just roll back, not break because of that. So you're kind of prepared for all these things that can happen in an embedded environment. You want to have atomic updates. So that means that the update succeeds or it fails. There's no in between, right? So you don't want to, I've updated half the system and then start that, and you kind of get weird behavior, you don't know why, and so on. So it's a pretty hard requirement. You want to do it. It either succeeds or fails. Basic integrity checking, especially if you're doing it over the air, you want to see that all the bytes arrived. Signed images, so you need like cryptographically be able to sign your images so that you can say they are coming from a trusted source, like from me, not the third party is trying to install. And you usually want some kind of like compatibility checks so that this image only is applicable to this device. So you're not able to like deploy by accident wrong image to the wrong device. So you want this built into the updater. And there are some ways that are accepted practices or common ways to do it. And one of the easiest ones, and that has been proven to work at large scale, is like for in the Android example, is something called image-based or block-based updates. So this is pretty easy to implement, test, verify, maintain. There are some downsides. I will go into this a bit more in the next slide. Incremental atomic image upgrade mechanism adds some complexity. Typically, you want this like over-the-air system is complex enough. So you want to keep it as easy or as simple as possible. It's not uncommon nowadays that you have containers. Some people use that as a deployment mechanism because it does have some built-in capabilities already to at least do like atomic updates of containers and so on. But this typically only covers the application part. So you cannot update the Linux kernel using containers. So you would still need another mechanism to do the update of what's underneath the container, so to say, the container runtime and so on. And package managers that, we commonly use on our PCs, like Debian, dpackage, and Fedora, and so on. These were not really designed for the embedded use case to handle this like power interruptions or network connectivity issues. And one of the biggest problem is it's not atomic. So you don't really know if you update a package, it has dependencies, it will update the dependency, you lose power, you don't really know where you are anymore and stuff like that. And it's hard to maintain since you have you need to all this dependency management and so on. Kind of want to avoid this. So I mentioned this image-based updates. So there's typically two ways that you do this. You have something called asymmetric image updates, and this was how Android did it before. And it's typically, if you ever used an Android phone or you get a notification, it says there's a new update for Android, you want to install it, yes, and then the device reboots in some kind of recovery OS because it has downloaded the image, placed it in a separate storage. You reboot to some kind of recovery OS, and then you're able to update this part. And you can also, if you get interrupted, you can always just retry because then you just boot back to the recovery OS. So there's fail safes in place for such an approach. But the downside is while you are doing the update, you have to boot into this, so the device is not usable, so you have downtime, right? And was pretty annoying on Android as well. It could take quite a while to do this, right? So that's one of the downsides of this approach. Any questions? Does this make sense to everyone? Yeah, great. So the other approach is, and this is how I think it's maybe optional, or it's this is how Android does it right now, and this is how they did in the Chrome OS, for example. This is how they deployed updates as well. And in this case, this is a basic like redundancy system setup. So you keep 2 copies of your whole system, or and as I showed before, this contains your distribution, the Linux kernel, the application. So you bundle it and you keep 2 copies of it. 1 copy is active, and 1 is always inactive. And when you do an update, you do it from the active one, so the system is operational and running while you do it. So you can do it in the background, and you are writing to this inactive partition, right? So there's no real downtime in such a case. Besides, once you have flashed this, you need to reboot and switch between these, right? So you go from this will become inactive and this will become active. You try it out. If it doesn't work, you always have the option to go back to the old active one, because you don't really touch this one while updating that one. But there is an obvious downside to this one as well. So there's storage overhead. Nowadays, I don't really see this being a big problem, because storage is fairly cheap, and we're usually like in gigabytes of storage on embedded devices, which it was not always like that. It was more constrained before.
So in the asymmetric case, you store the new image to the persistent data, and then recovery OS use that in order to install into the OS partition. As far as I understand.
On this one?
Yeah.
Yeah, so your main OS downloads an image from somewhere, puts it here, and that's how the recovery OS has access to it. Yeah.
Exactly. But in the symmetric case, you don't really need that, because everything is used or dumped from the active OS.
Yeah.
So do you need the persistent data at all?
Typically, you need this, especially for the update manager. So if you have some kind of if you want to keep states during reboots and so on, you need, but this is just to store state or log files or something. And also keep in mind that in this setup, your OS is basically stateless. So what you typically do is configure this read-only, right? So you don't want to do any writes, because once you update, it's all going to be gone. So anything that you want to save, like logs, or if you're writing data or saving data and so on, you want to do it on a separate partition, because otherwise you will lose it on each update. So that's one of the main reasons for persistent data. Any more questions, or does this make sense to everyone? Great. So quick comparison, coming back to these different methodologies, what they have and what they don't. So there's no perfect. There's always some drawbacks with all solutions. If we take, like we said, atomic, typically you lack this in Debian or these type of Deb packages and RPM. And that's why it's not really viable to use it, so they kind of fall out as an option. Consistency across your fleet is one of the big benefits of doing image-based update is, once you do an update, you always update everything, so you know what you are running on each device. And this is important once you start, like if you have 1,000, 10,000 devices, 100,000 devices, this becomes more and more important to have that you're sure that once I do this deployment, this is what I'm running. There's no question about, and this will not be the case in, for example, in Deb packages, or if you're using that kind of approach. you don't really know what's the state. Are two devices identical in regards what they are running? And also containers also has a drawback because it only manages, you typically only manage application or something using containers. So you could have inconsistency that the devices are running different underlying components. One important thing is, especially in these open source solution, is how well does it integrate with current workflows. So I mean, this is pretty Debian or this type of updates is it's familiar to people because you've used it on your laptop or if you have running Linux and so on. Image-based and symmetric containers maybe like between green and yellow. But there's some there's a new workflow you're introducing if you don't have image-based updates already. So there's some new things. Bandwidth might be important, or in most cases it's quite important. So it might be costly to deploy. The number of bytes you transfer from a server to the device has an effect on cost, right? So that's why these image-based approaches are pretty bad at this, because you are deploying the full image always. So regardless of what you are updating, you always update everything, even if you haven't changed it. But there are remedies around this as well for the image-based ones. Compression is one way of mitigating, using well-known compression algorithms to reduce the size of the image. But also deploying like binary deltas instead of, so you have two images, you compare them and you generate a diff and you only deploy the diff to the device. And then there are ways to, and I mean, there are tools for doing this. So it's not something that you typically would invent on your own, just reuse existing tools. So I want to get to talking about the ecosystem. And there are more, so I cannot really fit everything. There's a new solution every month, it seems. This, and I've done this talk once before, so this has grown a bit, this list. And you could basically break it down a bit. So there are these different type of solutions. And as I said, I focus here on open source solutions. There are quite a lot of proprietary solutions that focus like on automotive and so on, but it's quite hard to like get some information about them unless you contact them and request a quote or whatever. So I don't really care that much about that. So I'm focusing all of these solutions are some parts or in whole are open source. So there is a, and there are typically like different areas. So we have some like frameworks, as I call them, and these are not complete solutions. So for example, SWUpdate and RAUC, they are only clients that you, so it's an application that you install on your device. It doesn't solve the OTA problem for you. So it's just an installer on your device, which has they are quite feature rich, but you need to sort the server part on your own. In this case, there is something called libOS3, but it's more of a infrastructure tool than an updater, because it's a way of structuring. It's Git for root file systems, they typically say. So it's a way of constructing your root file system, and it works kind of like a Git repository. And it's not exclusively used for OTA or updates on devices. It's used in other applications as well. But it's like a framework you can use to build a solution, so to say. Hawkbit is a standalone server, open source server. So, and in this case, you need to, it doesn't have a client implementation. So you need to provide that client implementation or write it on your own. Or, I will get into this later, for example, these SWUpdate and RAUC, do have integration with Hawkbit, some kind of reference integration. And then you have OTA solutions, and these focus, and this is where Mender, which I work with, which focuses on solving the problem end to end. So it typically contains the client that you run on your device, some kind of a server backend, but also a management front end. So it's the whole chain. Then there are OTA solutions. I kind of broke this up because these are based on the frameworks here. So there are companies that use this SWUpdate and Hawkbit and created like a commercial product around it. So that's what these guys do. And then we have something I call full stack. And this typically involves containers. So there's a couple of solutions. But this is not exclusively OTA or like firmware updates. Because it's typically you need to run a certain OS and it needs to run containers. And but one of the components in these systems typically is that they provide also OTA, so you can update. So there's Foundry, Balena, and there's one fairly new Torizon that all work in a similar way. Any questions or comments? Have you heard of these before? Huh?
You have a demo?
Huh? Demo? Yeah. I can show you after that. Sure. Usually doesn't. I'm always ready. Okay, so let's. I'm not gonna go through all of them in detail because there's too many of them. But I will take a look at a bit on some of them. So SWUpdate is a Linux update agent with the goal to provide an efficient and safe way to update an embedded Linux system. And as I said, this is only the client side of things, but it has features that it works with these update type like symmetric or asymmetric image-based updates. It also is able to you can work with deltas as well, so using RDIF, for example. You can do in-place updates as well, so it has all these kind of features. And one of the more popular features probably is that it has like a local web server, so you don't have to insert a USB stick. If you're using this, it exposes like a web server that you can upload an image to the device if it's like connected. And this particular one is it's mainly written in C, and it's under GPL v2 license. And all of these that I'm going to mention, they do all have this, like the basic requirements sorted out, so you can cryptographically sign images, and SWUpdate even supports encrypting images. So it's not only signing them, but you can also encrypt images. And they typically have some kind of integration. So SWUpdate has like a reference integration with the Yocto project. If you're using the Yocto project, it also works with Buildroot. Rauk, pretty much the same concept, but a different company or different people working on the same thing. But also focuses on the client side things only. Both SWUpdate and Rauk integrate with the Hawkbit server, so they are able to communicate with the server, but it's two independent projects, so they don't really support Hawkbit, or so to say. Actually, this is wrong. I don't think they have this. But also with this, you can do symmetric, asymmetric image updates depending on how you configure the tool. They also are able to do a delta update. But they are using CA-Sync, which is a different algorithm or different way of doing deltas. And they also do signing verification and so on. But what these don't do is it's a tool, so it's not a complete thing. It gives you the tool set to implement updater, because you need a client that's running in your as an application, but there's typically bootloader integration. So to be able to switch between images, you do this in the bootloader. So you say to the bootloader, I want to try this new image, and this they don't typically include that. But it's a tool that you can use to. It has all the capabilities, but just nothing out of the box, basically. And Hawkbit, it's an Eclipse Foundation project, and it has sponsors like Bosch and so on. And it's a standalone server to manage deployments, basically. And it's written kind of in a generic way, so it doesn't really care about what kind of client is connecting. It exposes an API, and the client needs to implement this API, and then it can work with the Hawkbit server. It's Java-based completely, I think, which kind of nowadays it's not so popular, I guess. But and as I mentioned, SWUpdate and Rauk are example of clients that do have some kind of integration already, so they can work with this. And it's pretty feature complete, this thing. So it can do all the things that you want to do, to manage your deployments. It has reporting and some basic monitoring capabilities, rollout management, what I talked about before, that you can create phases of rollouts instead of deploying everything to everyone at the same way. And it also manages artifacts and so on, so you can get a list and so on. Any questions? No? So I want to mention this approach of, so we have Torizon, Balena, and Foundries, which are pretty much, they kind of do it the same way. But this is like a full stack thing. So you have some kind of base platform which is running Linux. You have a container runtime. They usually include an OTA service as well. But then you use containers for applications. So you can have multiple containers running. And for this part, you use the container mechanism to update these. And then you kind of implement some kind of service below to be able to update the container runtime and so on. But this has a lot of other, to be able to utilize this, you have to use everything. You cannot opt out of the container. You could probably, but this is not what it's. They are designed to be a complete package, while the other solutions are intended for integration with other frameworks.
Does this mean that if you use Torizon, you are, for example, not able to provide your own kernel?
You are, yes, but you are able to provide your own kernel, I would say.
So if I have some custom hardware and I have my own bootloader, my own kernel drivers, I could still plug those into Torizon and build my whole device around the Torizon ecosystem? Okay.
Yeah, so that should work with all of them that I mentioned earlier. But I know Balena is not fully open source, so I don't know if you can use all of the components. But I know the Foundries and Torizon. Torizon is based on Foundries, so it's definitely possible to add. But it's a package deal, as I said, while the others, like frameworks, and so these are more of integrating with what you have already instead.
So with Foundries.io, are you limited to the architectures they support? Do they support ARM, for example?
They do have some. Yeah, but you are relying a bit of what they are providing out of the box. Otherwise, you would need to do the integration on your own, which can be quite costly and time consuming, and maybe you don't want to spend time on that. It depends. But you are very reliant on what do they provide out of the box. And now it's time to talk a bit about Mender as well. So Mender, I've already mentioned that these, if we go back again to this, so we covered a bit of the frameworks, but these, so Mender is a solution, and it attempts to be an out-of-the-box solution. So it solves the client problem. It also provides a backend and a server and a management front end, and it's all open source, and it's under Apache 2.0. Everything is written in Golang for this project. And it has all the basic features that you would expect, and I don't need to go through them all, but it does only asymmetric image updates. So it's this AB or active-inactive OS switching. Binary delta is something that we are working on. That's gonna be, we don't have that yet. But it can also be extended using something we call the update module framework. So you can do image-based updates, but then you can implement your custom installers. You can install a file or a Tor archive or a proxy of firmware or something. So there are capabilities to extend how it works and operates. Integrity checks, of course. There's device groupings for controlled rollout. Secure TLS communication between server and device is provided. There's also like a authentication workflow to ensure trust between the device and server, because just because a device can connect to the server doesn't mean it gets accessed. There needs to be an established trust between the two. So that's also provided or built in. And we do work with like the Yocto project, Buildroot, Debian, Ubuntu, Raspbian, anything. As long as it's Linux, it works. And that's always been one of the goals of Mender as well. It should integrate well with others. So it shouldn't really matter what as long as it's Linux, it works. Yeah.
Does it only work with this Mender management server, or could you bring a USB stick or download from another device in the chain or something like that?
Yeah, so it does. On the next slide, I had like a bit more, but it does support. So we call it standalone deployments. So you don't have to use the server. You can implement like local updates from a USB stick or something like that. So that's supported. And one of the benefits of doing like an end-to-end solution is that you are able to test it all the way. So we do a lot of testing. I mean, quality is quite important if you're going to update someone's system, right? So you need to ensure that it works. And one of the benefits of offering everything, the whole chain, is that we can test it very rigidly to ensure that it's robust, it's secure, I don't really have that benefit of using these framework components, and you would need to implement your own tests and so on to ensure that it works. There are interfaces to adapt, like the update flow to application-specific use cases. So, for example, the client will write the image and reboot by default. And maybe you don't want to reboot, interrupting the user or whatever the product is doing. So there's an interface to like control the state machine of the client to say, wait with the reboot until I say you can reboot. So there's like integration with application and so on. And one important part of the server architecture is that it's microservices. I don't know, it's a buzzword. But the important part is it's API based. So all the functionality of the server, we do have a management front end, so you can like log in to the server and so on. But all the functionality is exposed through APIs. So the intention is should be fairly easy to integrate with if you have like another system that manages devices. You can integrate this. You don't have to use the management front end, or you can script And usually when you like reach 10,000 devices or 100,000 devices, you don't want to go to a web page and click things, and you kind of want it automated and scripted and so on. And that's where APIs come in. Yeah, so, and this applies, I mean, in general, I think, not just to Mender, but some of the benefits of using like open source components is, and it's fairly common that when we work with people, or there's less like reliance on tribal knowledge. So typically, you have someone that has written some kind of homegrown update solution, then that guy leaves and no one knows how it works. And that's kind of, if you're using an open source solution, there's always more people that know this system. And can always, especially if there are like communities, so you can ask people that are working with it. Yeah, and I want to talk about this last thing a bit. One of the problems if you're going to do integration is a pain for most people, because I mean it's a pretty low level thing if you're going to integrate with the bootloader. And that's why we focus quite a lot on, I mean, we are an open source project, we do have a community around the project and so on. But to be able to support, I mean, the embedded Linux market is so fragmented. There's so many different devices, boards, architectures. And so what we try to do is to utilize this. And we created a community around this. So we have like 40 plus like pre-integrated boards that are fairly easy to get started with. And that keeps growing. But it's important to do this, I think, because to get this, that if you do like board integration, that it gets fed back to the community, so other people can benefit from it. So we do have like a different, for Yocto project board, if you're using Debian or Buildroot or OpenVRT, there's some resource of, if you don't have, if your device is not on the list, you can probably use them as inspiration, like to do your own integration on them. And I think that's what I wanted to say today. So if you have any questions.